Okay, the next subject concept is four-point condition. That is also important, when we talk about a phylogenetic tree. But in this part, I shortly explain and roughly explain and see some several examples of four-point condition proper theorism, and I will explain how this theorism is related to tropical geometry. I focus on what is four-point condition is related to a tropical geometry. Okay, let's see the four-point conditions theorism. Let T be a phylogenetic tree and X, Y, G, and W be leaves. So if I plot the graph X, Y, G, W, and we can think about like this. We can phylogenetic tree, one phylogenetic tree. Then the relation, if 4-point is given, is that if we add dxyg, okay, then let dx, what is dxy, be the shortest path between x and y. So if we compute the distance dxg, that would be here, but this is to not shortest path, just connect this part. Okay, this is okay, but this is not shortest path. So dyw, the same reason, this here, we can add to sum, and that is always smaller or equal to smaller than, or that part is always bigger than the maximum between two distance. So the first thing is that the first part is that dxy, the shortest path, is like this, and add dgw, okay, some of this blue line, and that means that dyg, when you think about shortest path is here, and add dxw like this. So these two values is always greater or bigger than the purple, some of the purple distances. When visually that would be trivial. For the proof, computation proof, based on this node, let's put like this, okay, A, B, C, C, D, E, and compute. In that case, where A, B, C, D, E is the length of branch, all value must be positive. So based on by putting, so dxg means that A plus B. Okay, in this way we can, by changed its distance, we can prove the 4-point condition. For example, we can see a leaf structure, vein, so-called vein. When you observe the vein, we can see the following relation, like this. Red and white. White is better. Oh, this is white, white, white. Okay, not good. When you observe the vein, we can see that part is, we can observe the vein structure based on each point. Per point is fixed. Then we can see the following figure. That figure is similar to this 4-point, the phylogenetic tree that I explained. So we can check that in this vein structure, leaf on vein on the leaf, we can check that 4-point condition. And we can describe the phylogenetic model. For example, by using this DNA information, alignment of DNA sequences, the phylogenetic tree is well described. The so-called mutation, or how far by the alignment of DNA sequence we can plot the phylogenetic tree, that which species far and close between two species. Then in this phylogenetic tree, we can check that the 4-point condition. The detail of how we obtain the phylogenetic tree, like this, check that my Instagram homepage, scene 285. This is so complicated, so lack of time to describe all parts of this model. The second example is plateau problem of Stein problem. When we think about 4-point is fixed, then if we, for convenience, let x, y, g, and w, and we want to construct a load or all the 4 points is connected. For example, the scale is one way to connect it to the 4 point. It's every point, but I want the shortest point between shortest phase. When you consider the shortest phase, when you find the shortest phase between every 4 points, that is like this. As we saw this model, that is the shortest path on shortest path. Then we can compute by so-called calculus of a variation, but if we think about the point is fixed by like a pin, and in this plane, between this plane, inject a soap bubble into between two spaces. Then the soap film is soap film forms the soap film forms. Then this film suggests us the shortest path between between 4 points. In general, soft film always the shortest and minimum related to minimum surface and shortest path. When we observe in a plain soap bubble, that is sphere. Sphere is the minimum surfaces when volume is constant. Okay, soap film forms always the shortest and minimum ways to its film makes by shortest and minimum ways. That is related to when you think about the carotenoid, and in general that is a plateau problem. Anyway, we can check out the 4-point condition when you think about a soft film. The final example is understanding to 4-point condition as a tropical geometry. As I said, 4-point condition is written as like this: maximum dxy dgw dyg plus dxw. When we change this user addition and user multiplication as a tropical version. So in user sum is changed tropical multiplication, and maximum blah 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 AB, okay, per convenience AB, it means that A tropical sum B. So if we change the this 4-point equation, then the left side is like this, and the right part is changed by that is tropical multiplication, and the maximum is tropical sum. Okay, we can change the equation in a tropical version. Then question: if I set the star, what is star? That describes so-called Ptolemy inequality. If we consider following convex polygon, say A, B, C, D, then Ptolemy inequality means that in general rule, AC, the line segment, BD is ABCD plus BCDA. That is Ptolemy inequality. Then AC means that we can change DAC. Okay, change the DAC. Oh, so sorry. If we consider for the convenience, I will put that. Let's put the coordinate respectively X, Y, Z, and W. Then AC means that DXYG and BD is DYW. We can consider originally that is a multiplication is usual, but let's think about tropical multiplication. Then add AB means that DXY and change the tropical sum. CD, where is CD? Okay, that is DGW. Okay, then change the sum and the tropical sum. BC is DYG. And lastly, DGW, also XW, DA, okay, XW. So that if we change the 4-point condition into a tropical version, the result is a Ptolemy inequality. So in this respect, a 4-point condition is related to a tropical geometry. And surprisingly, when you observe the lip structure and the field is a tropical geometry. Okay, tropical geometry. And this is a leaves that is quite related to a like a leaf and natural phenomena.